So welcome everybody to our fourth and final regional forum for the Next Generation Urban Greening Project. This project will be wrapping up at the end of the year, so we're excited to have you all in this space for one more time. And today we'll be wrapping up some of the loose ends of the project and unveiling some really exciting work that's come about as part of this project. Next slide. So today we'll be talking about green stormwater infrastructure monitoring work that's been happening in San Francisco. Alicia Gilbreth and Jennifer Doherty will be talking about those projects. We'll then have an implementation project highlights by Lauren Chavez from the San Francisco Rec and Park Department. And then Lauren will dive into our regional framework for urban greening, which is one of the big deliverables for this project. And then Karen Verpeet will be talking about the Urban Nature Collaborative and the ideas surrounding that. And then we'll end today with a little bit of discussion time and a choose your own adventure for all of you to decide which discussion section you would like to go into. Next slide. So the overall goal for this Next Generation Urban Greening Project was to provide information and tools that municipalities, regulators, NGOs, and other stakeholders need to achieve more benefits through urban greening. And in this project, we've been really focusing on kind of a whole suite of benefits and really thinking about urban greening elements that can provide multiple benefits at once. And these include things like improved water quality, reduced urban heat, and things like additional habitat and connectivity as well. Next slide. And the way that we've been doing this through this project has been multi-pronged. So again, through this green stormwater infrastructure monitoring, we did a benefit quantification and spatial prioritization exercise called the Watershed Plan, which we presented in the last forum. Lauren Chavez and Will Logsdon have been working on multi-benefit implementation projects that SFEI has helped to inform in some cases. And then we've had these regional forums as well as the development of the regional framework. And so today you're going to be hearing about, next slide, 3 of these pieces that I covered in the agenda. So the GSI monitoring, a little bit about implementation projects, and the regional framework. So with that really brief overview, I'm going to hand it over to Alicia at this point to talk about the green stormwater infrastructure monitoring results. And Alicia is going to focus on the legacy contaminants. And then we'll have a couple of minutes for some clarifying questions. And then Alicia will turn it over to Jennifer Doherty, who's going to focus on the emerging contaminants. And again, we'll have a couple of minutes for clarifying questions. And then that discussion section at the end will be a time where folks can really dig into the results. So Alicia, over to you.
Okay. Hello, everyone. It's nice to be here with you. And I'm Alicia. I lead the Stormwater Monitoring Program for SFEI. Excuse me. I want to first set the stage just for the monitoring piece of this project to begin with. So we wrote this proposal in 2020, early 2020, and this was just on the heels of a really big microplastics project that we had completed, a pretty fairly sizable and comprehensive one for the Bay Area. And one of the key findings was that stormwater transported a huge load of microplastics and microparticles into the bay, especially relative to wastewater, which had been sort of a prior focus for microplastics in a lot of studies around the world. On top of that, about half of that load that we had seen in our study was tire wear particles. So this was kind of a big on the minds of a lot of people during early 2020. Excuse me. In addition to that, we had just completed a stormwater CECs, or Contaminants of Emerging Concern project, where we had collected a bunch of stormwater samples around the bay, and we collaborated with the University of Washington. And our partners at UW were hot on the trail of a transformation product chemical, a different emerging contaminant from tires that they believed was causing massive coho fish kills in the Pacific Northwest. They later published that study in later 2020, and where they highlighted 6-PBD quinone as causing these kills. And you'll hear Jennifer talk about that in the next presentation. But just FYI, we also call it 6-PBDQ or 6Q. And then finally, 2015 to 2020, the stormwater community was working really hard to figure out the degree to which GSI was going to play a role in meeting the total maximum daily loads requirements. And municipalities were developing and starting to implement their green infrastructure plans. But we had only, these are for PCBs and mercury, but we only had 8 to 10 small scale pilot projects monitoring bioretention for PCBs and mercury performance or reductions. And we really need a strong data set to base our strategizing and our planning and our accounting for progress towards the TMDL. So we needed more. Just to add to that, I want to sort of go over what are our motivations to monitor. Again, we need to develop underlying data to optimize where we put GSI, or sorry if I didn't explain that, green stormwater infrastructure. So I'll use the acronym GSI. So where we want to optimize GSI, where we put it, and then as well as how we design it. I already mentioned the PCB and mercury TMDLs. We have to be able to estimate our progress towards TMDL compliance. And then let's not lose sight of the fact that it's not just about PCBs and mercury. Green GSI reduces a lot of pollutants, and we want to start building the data set on reductions of microplastics and emerging contaminants, so that we know what we're getting in terms of performance for those new focus pollutants. There are a lot of different methods for measuring performance. I've listed some of the key ones. The bottom four, all of them except for the top, are really relevant here in the Bay Area, strongly relevant towards understanding how we reduce loads to the Bay using GSI. So Jennifer and I will each present, she'll present some of these methods. I'll present all of the bottom four. And because they give us different angles on how we understand the data and then how we extrapolate that data to think about other sites. We just getting to this study, we looked at 4 sites in San Francisco. 2 of them drain directly to the Bay, so into the MS4 and out to the Bay, and 2 of them drain into the combined sewer system. I want to note 2 key things about each site. So one is they span a broad range of age, from being completely brand new site in the upper right-hand corner, Cracker Amazon, to being as old as 11 years in service, Mission Bay Circle in the lower left-hand corner. Also, I have something written up there called the GSI to DMA percentage or ratio. What that means is the size of the unit, the GSI unit, relative to its drainage management area, all of the area that drains into it. Kind of a target that's often cited is 4%. That helps you treat a certain amount of the rainfall that comes in to your site, to your unit. But here you can see we've got a 2% site in the lower right-hand corner, Viz Valley, all the way up to a site that's 22% of the total area, which is Candlestick Point in the upper left. So we have a range of characteristics amongst these 4 sites. What did we do? We monitored at these sites. we sampled stormwater at the inlet and outlet. I'll explain that in a moment. We measured a variety of contaminants. The ones we'll present on today are listed here. Our collaborating firm, Lotus Water, modeled the hydrology at a couple sites. I'll present one of which today. And then we also did some soil profiling for PCBs, mercury, and microplastics. That's looking at the concentration of these contaminants within the soil themselves. So we got to do this during the summertime, and I'll go more into what that looks like later in the presentation. So again, we collected composite samples. That means we're collecting a little bit of water many times throughout the course of the storm at the inlet and outlet of each site. What do I mean by inlet and outlet? Well, this is Candlestick Point. We've got water flowing off the DMA, the drainage management area. It's coming kind of off this crowned street and down the curb, and it flows into this inlet here, which is also a curb cut. And then we are also monitoring kind of at that outlet port, there's a way to get to the outlet. So what we're monitoring is the water coming into the unit right before it goes in. So this is the untreated water. And then we're accessing the outlet after the water infiltrates down through the unit. It goes into a perforated underdrain. We access that perforated underdrain just before it goes back into the storm drain system. Okay, so I'll present on the suspended sediment, PCBs, and mercury results. First, I just want to talk about real quick how GSI works in bioretention specifically. There are many mechanisms for reducing pollutants or capturing pollutants in these units. The primary one, however, for the pollutants that we look at is filtration. So water filters through the soil media. It either infiltrates down into the native soil or it goes into a perforated underdrain and then back out into the storm system. This is an example at one of our sites where we looked at different filter sizes. We filtered the water through successively smaller and smaller filter sizes. So on the far left, those filters are capturing the coarsest particles, and to the right, the small is the smallest filter. So it's capturing smaller and smaller particles as you go to the right. And what you can see is at the inlet on the top row of filters, you get coarser particles, you get more sediment, and then at the outlet, you have fewer particles, and they tend to be smaller. So the coarsest particles are filtering out. Your finest particles may still be getting through. And note these, I acknowledge this is not an extremely wonderful set of photos. It's the filters are wet, so it's a little less obvious, but hopefully you can see what I'm explaining. Okay, so I'm going to show you the concentrations just for TSS, total suspended sediment or solids, PCBs, and mercury. And those are the three pollutants I'll focus on. And so I'll show you the concentrations at the inlet, which is the blue bars, and the concentrations at the outlet, which is the green bars. So for Viz Valley on the far left, you've got a 93% reduction from inlet to outlet in concentration. Candlestick Point, still pretty good, not as great. But notice the inlet concentrations are a lot lower to begin with. And this is going to be a point I bring up subsequently. Crocker Amazon has decent performance, not as good. Now, remember, Crocker Amazon is a brand new site, and this is consistent with what we see in the literature, where brand new sites, they tend to leak some of the soil media that is already in the unit. So it's not necessarily leaking pollutants more, but it's leaking some of the clean soil media. So the the suspended sediment that we're measuring here, that I'm showing you results for, is not as strong, but pretty good still. And then Mission Bay Circle was a unique case. We're seeing high increases in concentration at the outlet. And what's going on there is there was seepage into the outlet port from unfiltered or untreated stormwater, as well as kind of other stuff that it picked up in the unit. So basically, there's a commingling effect here. I didn't want to exclude the data because we're not supposed to do that, but there is this commingling aspect that I really want to highlight here. And it's interesting because some sites there will be commingling. What's really important in Mission Bay Circle is it was only a trickle that was actually coming out that we were sampling out of the outlet. So if you estimated loads from the inlet and outlet, you're still getting a lot more sediment coming in than going out. Because you just have a trickle, even though it's more concentrated. Okay, sum of 208 PCBs, so this excludes PCB 11. Sorry, let me move this. Okay. Similar results. Candlestick Point, the second one in, not as good of reduction. Again, note super low concentrations to begin with. So there's this phenomenon called an irreducible concentration. That means you get your outlet concentrations can get so low, and your inlet concentrations can get so low that you can't go any further in terms of reducing concentration. So I think that that's what we're seeing at Candlestick Point. It's just generally a pretty clean drainage management area coming into it. And then finally, sorry, let me move you guys again. I got to do that. Okay. Finally, we're looking at total mercury. Mercury is a little more complex. So remember, we noted in the previous screen that there's a lot more coarser particles that get the coarser and more particles collect on the filters, get filtered out going through the treatment of the GSI unit. Total mercury tends to absorb to finer particles. It also tends to be more in the dissolved phase. So total is showing both the particulate and dissolved phase mercury, but a bigger proportion of that is dissolved. So it's the reductions are not as strong as what you see for PCBs or sediment. You're still getting reductions at the first three sites. So here's some potentially key factors, and this is both what we are seeing in this study, but also what we've learned from several of our previous studies on bioretention. How high that inlet concentration has a big impact on how much reduction in concentration you can get. Again, we'll highlight this in the next few slides. The age of the unit may be important. So I mentioned Crocker Amazon, brand new. We're seeing less performance there, a little less. It's still working well. Are we getting full treatment, or is there commingling like we're seeing at Mission Bay Circle? And then also that particle size and fractionation between dissolved and particulate is key. Now I want to introduce you to the performance curve. So this is showing the inlet concentration across the x-axis and what your percent reduction is at the outlet between the inlet and outlet. So basically what you're seeing for PCBs is that as your inlet concentration gets more and more polluted, gets higher, your reduction in concentration gets better and better. This is the trend. You can see the trend line shows that really clearly. Also, sorry, I should have mentioned all these points. These are sites around the Bay Area that have been monitored for PCBs and mercury and bioretention. The blue ones are from previous studies done by SFEI, Caltrans, the municipalities, and the county programs. The orange ones are for this study. I've excluded, in this case, I've excluded Mission Bay Circle, because it's confounding with that commingling aspect. But here what you're seeing is CP, Candlestick Point, where there's very clean concentrations. It's not getting a lot of reduction. Crocker Amazon, excuse me, the brand new site, it's operating kind of as expected. And then Visitation Valley is relative to the other sites around the Bay Area and relative to the trend that we see, it's actually operating better than expected. For suspended sediment, this is a little less clean graph, and this has to do with that aspect of whether the sites were monitored when they were freshly constructed or have a little more maturity. And we've teased out these dots before, and there's a pretty clear pattern there for age of the site. But in this case, I've lumped them all together. Crocker Amazon on the far right is performing not as well as the overall Bay Area trend, but again, that's very strongly, I believe, related to the age of it. And it doesn't have to do with pollution, it's just the soil media leaking out. That will change as the site matures. Candlestick Point and Visitation Valley, the two above the line, are operating better than expected. So I think the age of the unit and the soil media may play a really key role in this graph. And then finally, for total mercury, we are seeing overall the percent reductions are less, which you saw in that previous bar graph as well. You're even in the lower left-hand corner, you're even getting some increases at the outlet. And this is due to the fact that a lot of mercury is in dissolved phase and it's on finer and finer particles. And just looking at concentrations can be a little misleading because it doesn't bring in the idea of volume, the volume of water, and you need volume and concentration information on both to estimate load. Or load is a function of both concentration and volume. So if you may get higher concentrations at the outlet, but if you still have a lot less water, you can still have less load. Speaking of load, so our collaborating firm, Lotus Water, did some modeling for us for Visitation Valley, one of the sites. This is the site, I'll note, that was a 2%. Where we monitored it, it was only the GSI unit was 2% of the size of the whole drainage management area, and so undersized at the place where we monitored it. I will say the entire unit does meet that. It's about 5% actually, but anyway, where we monitored it. So here we're looking at mercury and PCB loadings at the inlet and the outlet at Visitation Valley. And in the I guess middle row for water year 2023, which you guys remember was a huge water year here. There was a total of 38 inches of rainfall, almost double what's normal, or what has been normal in the 5 years preceding our sampling there. There was a volume reduction of 28%, which is a key factor for City of San Francisco because of their combined storm sewer system and the desire to decrease volume. For the rest of the region, the key is decreasing pollution because there's not a combined sewer system. I'm not saying that volume is not important, but it's less. So what we were seeing, if we average, or if we estimate the mercury reductions from inlet to outlet in sort of your average year, you're looking at about a 64% mercury reduction. This is in load. And for PCBs, it's greater. It's 88% at Viz Valley. And again, I just want to emphasize this is an undersized unit. So a larger unit relative to its drainage management area is probably going to capture at least more volume, which in essence will translate, if you have similar concentration reductions, it's going to translate into a greater load that has been reduced. So really great results at this site, despite it being undersized. And last, I just want to get into the soil profiling real quick. So soil profiling, what this is it's taking soil samples at different depths of the GSI units and analyzing them for PCBs and mercury. We also did microplastics, which Jennifer will talk about. We measured right at the inlet, right at that curb cut opening, and then we collected kind of a composite sample throughout the rest of what we call the body of the unit. And we measured at these various depths, these 5 different depths, or 4 depths, and then the inlet. Right there is the inlet. And what I'm going to show you, there's a few reasons to do this kind of sampling. And the one that I'm going to focus on is this idea of how much is building up in the system and, what its implications are for maintenance, but also this concept. And I bet I'm not the only one who's heard this, but the question of are we by implementing GSI, are we putting in many toxic waste sites, sites that are concentrating pollutants and then creating these sites that are really problematic? So I want to address that here for mercury and PCBs. So the EPA screening level for residential soils for mercury is 0.71 and PCB is 0.23 milligrams per kilogram. These are extremely conservative guidance. They are not triggers for remediation, but they are some screening levels that would suggest maybe some further investigation would be good. And there are other trigger criteria. It's pretty complicated, and I'm still trying to get my head around it. So I just want to show the data relative to these super conservative guidance screening levels. And when I say conservative, what I mean here is that for PCBs, which is has cancer risk, what this screening level represents is a 1 in a million chance for people who would eat 100 milligrams of the soil polluted at this concentration every single day for 70 years. So that's really conservative. So what I'm going to show you, based on the concentrations that we saw in the soils for mercury, I'm sorry. These are not the concentrations. These are the years that it would take to reach the screening level for residential soil at each of these sites. That's based on the soils, the concentrations that we saw in the soils at these sites, and the number of years that they had been in service. So I'm just looking at the very surface at the inlet, and then the top 4 inches, basically. 0 to 50 millimeters is about 2 inches down, and 50 to 100 millimeters is about 2 to 4 inches down. So these are the number of years. So I'll highlight 2 of them. If we think the typical service age of a bioretention site is around 25 years, then we're looking at 2 instances where it would take less than 25 years to reach that super conservative EPA RSL, residential soil level. And then for PCBs, there is this one instance right in the front at the inlet of Mission Bay Circle. So But basically, for the most part, none of these are going to reach uh, the RSL for during their expected life. And I just want to consult my notes because I want to make sure I make the right point here. I think overall this is really, really good news, because even though these units do concentrate pollutants, each site itself is just really not a mini toxic waste site. With normal maintenance, there will be turnover of that soil or dilution of that soil with additional amended soil before it reaches those levels. But a second point is that, as we develop a really regional data set, a decent data set of soil profiles in the region, let's say across 20 to 30 sites or something, as a region, we do want to develop some guidance on how often and where within a unit we should collect a soil sample, get it tested to see if we're maintaining them well enough that they are not reaching any sort of level of concern. And so for this example, for PCBs, you might say we should address that inlet, either by cleaning it or replacing the soil or testing it every 3-4 years, maybe 5 years. But again, this is ultimately extremely good news. I think and more study to be done, but this is great. Key takeaways. Mature green stormwater infrastructures, especially the older ones, are very effective for capturing sediment, PCBs, and mercury. Undersized units can still significantly reduce stormwater contaminants and volume, for that matter. GSI works better. Excuse me. GSI works better in terms of concentration reductions for higher pollutant, for inlets or drainage areas they're putting in higher pollutant concentrations. This is really key in terms of GSI siting. If your goal is to reduce pollution, then you want to put it in the most polluted areas. That may not be your only goal, though. In a lot of cases, it isn't. There are multiple benefits for GSI, of course. But if water quality is one, that's definitely what you want to look for. And then GSI in urban settings, several urban settings that we've studied, it's not creating many toxic waste sites. With that, I will pass it on. Oops, no extra slides needed. Let's see, stop share.
Yeah, and we'll just roll straight into Jennifer's presentation on emerging contaminants and hold comments till the end of both.
All right. Good afternoon, everyone. Can you all see my screen okay? Perfect. You've gotten a little bit of this background already, but I'm just going to go through it again. So green stormwater infrastructure is usually implemented to reduce runoff and address the regulated contaminants, like what Alicia was just talking about. Addressing emerging contaminants can also improve water quality, and contaminants of emerging concern, which is how we come to the acronym of CEC, are not well-regulated pollutants like PCBs and mercury, which we can think of as in the rear view mirror. Instead, with CECs, we're looking into the horizon, identifying unregulated or underregulated chemicals that can get out into the environment and harm people or wildlife. There are thousands of CECs, and it requires some detective work to select which ones to study. These contaminants have not frequently been monitored in bioretention systems. So tire particles are one emerging contaminant of concern for bay health. They are a type of microplastic, and our team estimates that more than 3 trillion of them enter the bay each year. There are no TMDLs, and they contain toxic chemicals which are released, including 6-ppd quinone. Tires with 6 ppd were listed as a priority product in 2023 by the Department of Toxic Substances Control, and tire manufacturers whose products are sold in California are now responsible for finding less toxic alternatives to 6 ppd. Green stormwater infrastructure is important for treatment while those regulations come online. So this growing body of evidence tells us tire particle toxicity is complex and driven not just by exposure to the particles, but also the chemicals that the particles contain and release. One example, and again, Alicia did a nice introduction for me on this, but one example is the tire ingredient 6 ppd, which keeps tires from cracking. It transforms into 6Q, is what I'm going to call 6 ppd quinone, and has been shown to be the causative agent for coho salmon fish kills in the Pacific Northwest. This led to the EPA freshwater screening value of 11 nanograms per liter to protect keystone species like coho. It can be hard to understand what a number so low means. So if you were to take about half a drop and put it into an Olympic-sized swimming pool, that would give you roughly 11 nanograms per liter. And that can show you just how toxic 6Q happens to be. So though coho are not typically found in San Francisco Bay, rainbow trout has been shown to be sensitive to 6Q as well. And rainbow trout is the same as, well, steelhead, which is a threatened San Francisco Bay species. So it's still very early in the study of emerging contaminants in GSI, and the contaminants we selected have a range of chemical properties that can inform retention and are from a variety of sources. They include 5 tire and road chemicals, including 6Q, the known chemical to kill coho salmon that I mentioned just a minute ago, as well as the actual tire wear particles. 5 pesticides and preservatives used in paints, pet flea control, and to control vegetation. And we also included 3 drugs like allergy medicine and caffeine. To be clear, we looked at some pesticides, drugs, etc., but not all. That would require the use of non-targeted methods. So the behavior of these environmentally relevant chemicals has not been studied comprehensively in bioretention systems. And we looked at how well they were removed from the 4 rain gardens that Alicia introduced in San Francisco. So let's turn to the results. When we break performance down by contaminant type, we see some variation. I'm presenting the averages for each group and also overall, roughly 58% if we go across groups was the removal. So many contaminants have high removal, but a few have very low or negative removal, and that pulls down the average. Tire wear particles were removed most effectively, followed by tire and road chemicals. You can see the 6 ppd quinone removal rate. I just graphed it so you could see that relative to the group as a whole, as that was more effectively removed. So the pesticides and preservatives showed the lowest average removal, and then the drugs were very similar to the tire and road chemicals. Next, I'll show you how the 4 sites compared. We're going to take it in 3 steps. So first off, site is shown across the bottom in alphabetical order. On the left vertical axis, we have the average removal for all storms at each site. There are 2 different contaminants. 6Q is shown in lighter green, and tire wear particles are in darker green. Starting with 6Q, we can see a dramatic difference in removals between Crocker Amazon and the rest of the sites. As a reminder, that site is the newest unit constructed, and this was sampled in the first 6 months. This less effective removal has been documented in the literature, and removal should improve as the unit ages. Alicia alluded to this earlier in her talk as well. Secondly, the vertical axis on the right shows outlet concentrations in nanograms per liter, and the X's show the average outlet concentration for the sites. Though we generally see high removals of 6Q, the protective threshold, again, that's that half a drop into an Olympic-sized swimming pool that I mentioned earlier, is low enough that the average outlet concentration from three of the sites is still above that toxicity level. And then lastly, in addition to site-to-site variability, we see variation in removal between the tire wear particles themselves, which are removed by filtration, and the removal of 6Q, one of the tire chemicals. Here we're back to looking at the sites together. This figure shows a simple way to visualize the treatment, how much is left after the water passes through the system. The gray bars represent what comes in, always 100%. And the green bars show how much is left after the treatment. For tire wear particles, 17% of the incoming amount remains, so 83% are removed. For tire and road chemicals, about 38% of the incoming amount remains, meaning that 62% are removed. For the drugs we monitor, the results are very similar to the tire and road chemicals, as I mentioned earlier, while for pesticides and preservatives, a larger fraction remains, roughly 60%, which reflects their lower removal in these systems. As Alicia mentioned, there are multiple ways to measure treatment performance. Here we will compare two metrics for the Visitation Valley site. So concentration removal looks at how much the pollutant concentration drops between the inlet and the outlet, shown in green on the left. And then load removal, which accounts for the total mass of pollutant moved by the stormwater, which is concentration times flow, shown in purple on the right. We have flow information at the Visitation Valley site, and that is what is shown here. So we can compare these two metrics, and we see average load removal is higher than average concentration removal, around 94% versus 75%. This happens because bioretention cells reduce both concentrations and the total volume of water leaving the system. So in terms of total pollution prevented from reaching the environment, this system performs well. Regardless of which metric you use to describe the data, removal is high. We also looked at what's happening in the soil media to assess contaminant transport and capture within these systems. Tire particles are a special type of microplastic that are isolated and counted separately. So here I'm showing you measured concentration of tire wear particles by mass on the left, and microplastics by number on the right in soils from 3 color-coded sites. Data represent soil concentrations from inlet locations. Those are superficial soils right at the inlets, and soil core samples collected within the treatment cells at 4 depth intervals, down to roughly 30 centimeters, which is about 1 foot. Tire wear particles and microplastics were found mainly near inlets and in surface layers. Concentrations drop quickly with depth, indicating limited vertical migration. That's encouraging. It means that the media are effectively retaining particulates. However, accumulation over time has implications for media lifespan and maintenance frequency. And so to wrap up, overall, these systems perform quite well across a broad suite of emerging contaminants, even under the variability of real storm conditions. The one compound that stands out is 6Q. It remains detectable at toxicologically relevant levels, meaning source control is an essential part. Going forward, we suggest routine soil analyses to understand how long these systems can function effectively before media replacement. And this is the most comprehensive study of its kind, and it shows that green stormwater infrastructure is a strong tool for water quality improvement, but we need to pair it with upstream pollution prevention, like the source control measures underway with DTSC. And that's all for me.
Great. Thank you both, Alicia and Jennifer. We'll take a couple of questions now, and then again, we'll have a discussion section devoted to this part of the forum. So if you can find it, please raise your hand. It should be under the React button at the bottom of your screen. You can also type your questions in the chat. A couple of you have been doing that. Yeah, any burning questions for Jennifer or Alicia based on the green stormwater infrastructure monitoring results?
Melissa, should I be looking at the chat for questions?
There is one question in the chat that I have answered, but if anybody else wants to chime in, Bob Hall asked about testing the plants and whether they're absorbing or purifying the contaminants and whether these leave the plants through transevaporation or get transferred to any insects that may eat the plants.
I'll attempt a terrible. So we didn't test the plants, as Melissa said. It is a good question. We don't know. We haven't looked into this in the Bay Area yet about mercury and PCB specifically. Although I said filtration is a key kind of the major mechanism for reducing pollutants, we also know that there is adsorption and absorption into roots and plant and up into plant matter. So, but I don't know how much.
Great. And then, yeah, maybe Jennifer or Alicia, do either of you want to give an update on the DTSC efforts to do source control for 6Q?
I can describe where it's at in the process, if
Great.
that's kind of what we're after. But so I don't know how familiar everyone is with the process that DTSC goes through, but they first the first step is to list something, a contaminant of concern, and then the manufacturers have a period of time to respond by doing a series of testing to find alternatives. So let's see. So the priority product notification was set up November 30th of 23. After submitting their priority product notification, that means that they sell tires in California. They have the option to submit one of the following things by March 29th, 2024, which is a chemical removal intent or confirmation, a product removal intent or confirmation, a product chemical replacement intent or confirmation, preliminary alternatives analysis report, or these alternative reporting options. So I saw a bunch of talks at CTAC from some of the tire manufacturers. So they are still in the process of trying to find alternatives for 6 ppd. And they have a list of chemicals. Some of them are other PPDs, 7 ppd, 9 ppd, etc. And others are various. So there's not been a definitive action taking place, but it is in process.
Great. Thanks, Jennifer. All right. Tom, do you have a quick question while Lauren brings
Yeah,
up the
it's
slides?
probably
We need
not
to
quick,
keep
but I'll
moving.
just tell you what it is, and perhaps I can talk with the team offline. But first, just FYI, I noticed that you mislabeled graphics. You had suspended sediment concentrations as nanograms per liter versus milligrams per liter. Just FYI, it might be
Thank you, Tom. Sorry about that, y'all.
well, it's hard for you to see the M versus the N, probably by habit. My question was going to be about how you modeled flow, because I can understand how you can model inlet, but I don't see how you can model outlet flow. And of course, how much infiltration one gets is a big part of how performance of these systems. But I was kind of confused about you saying you didn't do any measurements, but you modeled flow.
Yeah, so these systems are lined and there's an underdrain. And SWIM, the stormwater management model,
Okay,
has option. Yeah, go ahead.
no, I understand. So well, go. I shouldn't have cut you off, but yeah, but you did point out that all these particular ones have underdrains, which is not uncommon in the Bay Area due to clay soils, but depends on the setting whether how much infiltration you might get versus. Yeah, so that's good enough for me right now. I mean, I think you got to move on.
Yeah. Okay, great. Thanks, Tom. Lauren Chavez, do you want to go ahead and share your screen? So Lauren is going to share some updates on implementation projects that the San Francisco Recs and Park Department has been working on. And Lauren is a project manager at SFRPD, and we'll be talking about some of the projects in McLaren Park that have been happening over the last few years.
Great. Here we are. Can you see?
We can, the slides are not in slideshow yet.
Okay.
Yeah, there you go.
Oops.
Now
Okay.
it's in presenter mode, so you might need to
Sorry.
switch your
Sorry.
Okay.
Melissa asked me to get ready for this more in advance and I didn't. Okay, let me get, I'm not sure what's going on. Let me share again. Gonna do it this way. Can you see now?
We can, it's still in the presenter mode.
Okay.
I think if you, yeah.
Yes?
Yes,
Good.
perfect.
Okay, great. Okay. Thanks everyone. Yeah, Lauren Dietrich Chavez with San Francisco Recreation and Parks. Happy collaborator on this next gen urban greening project. So one of the projects that I manage here is the McLaren Park Priority Trail Improvements Project. And this trails project has 4 priority areas. If folks are familiar with McLaren Park in Southeast San Francisco, we have a scope of work at the upper reservoir, kind of where our new Shelley Promenade starts at the northwest of the park, in the Shelley Loop inner core area, just south of Jerry Garcia Amphitheater, around Jerry Garcia Amphitheater, in what we've been calling University Hill, in the area between Lewis Sutter Playground and the Tai Chi and tennis courts up near Mansell. And then the Visitation Avenue corridor down in the southeastern corner of the park. And so we were able to collaborate with Estuary Institute on 3 implementation projects. And like Melissa said before, the San Francisco Estuary Institute were able to collaborate with our design team and our Natural Resource Division operations staff in plant palette selection for for these areas and helping us kind of understand the historical ecologies in these 3 implementation areas. And so I'm going to go through them from just in time that they were actually implemented. This project is nearing substantial completion, but some elements happened earlier than others. So we're going to start with Visitation Avenue in the southeast and then move to the inner core and then to the upper reservoir. So Visitation Avenue, we actually had our project scope included some trail work and planting and signage kind of all along this corridor. And we worked with our our partner's goal, growing outside and learning, spearheaded by the wonderful Fran Martin, who's advocated for green infrastructure and native plant installations throughout Visitation Valley. And so working in collaboration with Fran, our team helped to design and install a native plant garden and the associated trails that provide access to it. So I'm going to, these first set of photos are kind of from the, I don't know, can you see my cursor moving?
We can. Yep.
Okay, great. So so this first set of photos are kind of from this area just to the northwest of the garden. And this is what the site looked like back in late 2022. There were a lot of non-native trees and trees at the end of their life, as well as some dead trees, fallen over trees, a lot of invasive plants, and it was a site that our operations folks experienced a lot of camping and squatting, and there were a lot of feral cat homes in there too. This is a site after tree removals and initial planting. And this is what it looked like after a year of growth. I think it's quite a beautiful place to visit. I highly recommend it. And goal is does a lot with organizing volunteer groups and students to get out and enjoy this space and learn about native plants. And we're working on some signage installation to help people understand the historical ecology, as well as spot the native plants that we are planting here and elsewhere throughout McLaren Park. I added this slide because one of the things that Alicia was presenting on was this Visitation Valley rain garden here. It's a SFPUC asset on Recreation and Parks property. And I just wanted to mention it because, right, we're all sharing lessons here. And the picture on the left shows some sandbags that had been placed along the curb line at the drain inlet that goes to this rain garden because previously the water in a major storm event, the water had kind of jumped the curb. And so there were some sandbags there. But then in a rain event in November, a vehicle happened to be parked right above this drain inlet and curbed its wheels on the somewhat steep hillside of Visitation. And the water jumped the curb in a quite intense stream and cut like a Grand Canyon down through our new trail. So we are working on mitigating for that and planning for that. And so just keep in mind, like sizing of drain inlets, especially with more intense storms coming our way due to climate change, and also just protecting those areas, particularly on steep hills, to make sure that there's no parking zones, which we will be adding shortly. Okay, going to our inner core area. south of Jerry Garcia Amphitheater. So you can see here our scope for the implementation project was focused on this area where we decommissioned a social trail that had that our operations team had tried to decommission multiple times over the last 5 years, and it really took some significant disturbance and reshaping of the area in order to help park users understand that this is a very precious riparian zone and one of the three open creeks here in San Francisco at the headwaters of Gray Fox Creek. Please don't run through it or bike through it or let your dogs tromp in this area. And so the emphasis of the project was doing that restoration work. We actually didn't do anything right in the channel in order to avoid CDFW permits. And however, decommissioning the trails like from top of bank up and doing tree removals and replanting in this area were our scope of work. So these are some before pictures. I'm not as organized as I was on the other one, but you can see that just how densely wooded it was with some of these taller stature cypress and pine trees around the area. This is one photo from the south looking across to the amphitheater through that more wooded zone. And this is a photo from a similar location showing like just how much more sunlight is now landing in this riparian area in order to support the plantings that we did as part of the project. This is a different vantage, so looking from the opposite side of the creek down kind of on the amphitheater side, looking back up towards the headwaters of the creek. And just keep an eye on this tree here in the back here, because you can see how much this area how much we cleared out the trees in this area in order to make space to allow the sunlight to come in for the plantings. This I just threw in so you'll recognize it, the oak tree and the split rail fence just south of Jerry Garcia Amphitheater. The amphitheater's off here to the right. If you ever go to a free event there's a lot of them. I recommend it. You can go and check out the progress of these little baby plants that we put in. We grew them with with the Estuary Institute's plant recommendations for this riparian zone. Our Natural Resources Division propagated these plants from hyperlocal San Francisco genetic seeds. And then moving on to the upper reservoir. So our scope here, we had been a little bit more ambitious in terms of like we were thinking of cutting some massive swales in the hillside here, as well as removing an asphalt ditch and replanting in this zone and doing some restoration work and erosion control in areas where there had been previous social trails and utility cuts for other projects that were causing a lot of problems downhill. And we modified that scope in our design and bid process to really focus on the drainage corridor itself. And so I'm showing this picture. It's maybe a little out of order. Maybe I'll toggle this way. So this is on Shelley Drive looking up this drainage. And you can see from this photo from back in April 2022, with the rain falling, just like how much water's kind of gushing down and also how much sediment is in that water. And this must have been a mild storm because, oops, let me go back, because you can see across the way, you can kind of see the residue from some scouring that had then led to social trails and compaction directly across the street from this zone. I think I should mention, so again, here at the bottom of our drainage, we ended up just digging a pit. I think I heard someone mention this before. I think Alicia mentioned, that you lose some of your soil from your green infrastructure installations in the first year. And we knew just timing wise and with the contractor that we were working with and the timing of the rains, we were like, let's just put in a little safety net here. And so we just dug out a pit at the bottom that was really close to the road where our equipment operators could come in and remove sediment from this trap in the future. And so we did that in July. And after the first storms in November, it was quite full of sediment. And now we're working to get it completely emptied out because it's almost completely full after the more recent storms. And then I'm sorry, I don't think I have the photos after this, but there is now a lovely punch-in and a whole series of check dams coming down the hillside here that our team is going to be planting within the next couple of weeks. And so I definitely recommend coming to look at this. Look at this area. The intention was to slow and sink the water that's coming off the drainage for the upper reservoir parking lot to help just recharge the water underground, to provide clear water spillage onto Shelley Drive instead of sediment-filled water spillage onto Shelley Drive, which is already working. And then to enhance habitat with this sort of seasonal wetland that we're creating here. So yeah, come and look at the punch-in the future. I think I didn't add sorry, I ran out of time. But I'm happy to take any questions if anyone has questions.
That's great. It's exciting to see these projects coming together, Lauren. Thanks for sharing. Maybe just a quick question for Lauren.
Maybe while anyone's thinking of a question, I'll just mention too that it's, Melissa needs to bug us for documentation and invoicing and whatnot. And it's really a honor and a pleasure to collaborate and be able to support this research by like matching our project funding with so that you all could get funding to do this next gen work.
Well, thank you, Lauren. Yeah, and Will too. Working with both of your agencies has been really great for us. And, we've learned a lot by working with you. So yeah, thank you. Back to you as well. Great. All right. So we're going to move into the next part of the forum, and this is going to focus on the regional framework, which Lauren Stoneburner, who's an environmental scientist at SFEI, is going to present. And then that's going to kind of roll straight into the Urban Nature Collaborative that Karen Verpeet, also at SFEI, is going to present. So we're moving a little bit away from monitoring and projects and into the framework and next steps. And again, then we'll go into breakout groups for a discussion after that. So Lauren, I will hand it over to you.
Great. And you can see my screen?
Yep, looks great.
Great. Well, yeah, thank you, Melissa, and hello to everyone. My name is Lauren Stoneburner. I'm an urban ecologist at SFEI. And I'm very excited to be introducing our hot off the press regional framework for the next generation of urban greening. It was co-authored by Melissa, myself, and others at SFEI and funded by the US EPA Next Generation Urban Greening Project. This regional framework aggregates best practices and resources that can help the Bay Area plan and build the next generation of urban greening projects. So I'm going to be starting by summarizing the needs and challenges that first motivated us to develop a regional framework. I'll then walk through what this regional framework is, and then we'll dive more into how regional collaboration is an essential missing puzzle piece that could catalyze more benefit-rich projects. And since urban greening can mean many things in different contexts, what we mean here is nature-based solutions in urban environments that mimic natural processes and deliver multiple ecological and social benefits. It's often referred to as green infrastructure, green stormwater infrastructure, stormwater management systems, nature-based solutions, or low-impact development. And urban greening can range from highly engineered features like bioretention systems and green roofs and walls to more natural, less designed landscapes like parks, trails, and greenways. And I'm almost definitely preaching to the choir here, but as many of you know, when urban greening is done strategically, it can provide multiple overlapping benefits like climate resilience, cleaner air and water, biodiversity support, social and health benefits. And so this potential for one project to generate multiple benefits is important in the context of a growing paradox that cities are grappling with. On the one hand, cities have a great need. Cities need to urgently adapt to climate change, pollution, human health concerns, biodiversity loss, just to name a few. And then on the other hand, cities also face great constraints. Cities are space limited, navigating competing demands, projects are expensive in cities, and resources are stretched thin. And so because of the great need and great constraints, we ask a lot of our urban greening projects, and we expect them to serve as critical infrastructure that delivers on multiple objectives. So to make the most of each opportunity, we need more intentional planning and design. And the scale that projects are planned at can impact those project outcomes. So planning at the site scale is inherently essential for every project. It allows for precise assessment of what's possible and what's needed. And also, project planning shouldn't start and end there at that site scale. Because greening relies on nature-based systems, projects are often interdependent on one another to function. And so planning at that larger city or county scale can plan a connected network of projects that work together in concert. And planning within a single jurisdiction, like a city or a county, is easier in many respects, but there are big benefits to going beyond political boundaries. Planning at the watershed or landscape scale takes more effort, more coordination, but it also allows entities to pool resources and improve consistency across boundaries. And these entities can also work towards managing and repairing a full interconnected system and addressing underlying causes rather than treating symptoms or applying partial remedies, and therefore multiplying the benefits of each individual project. But planning at the landscape scale, especially across jurisdictions, is challenging. And just to name a few reasons, there are limited and unequally distributed resources like staff capacity and funding, guidance, data and tools. And it's also challenging for agencies to go beyond their core defined jurisdiction and mandates and objectives. And it's difficult enough to coordinate between agencies, let alone between jurisdictions. And urban greening is also planned, budgeted, coordinated, operated, and maintained within these systems and decision-making processes that were built for gray infrastructure. So the case for urban greening and these common challenges are almost definitely familiar to many of you. And in some ways, we're actually swimming in information and resources as we're all trying to find solutions to common challenges, but then can't find what we need when we need it. It's scattered across the internet or in institutional memory, and not everyone has access to the same information. So in order for us to understand what practitioners need to have the information and resources at their fingertips, we have convened 3 prior regional forums, just like this one, to gather information. We've interviewed practitioners and we've consulted with a design advisory team. And so using all those inputs, we've developed this regional framework for the next generation of urban greening. So this is a diagram of the framework. It dissects urban greening into 9 major steps, from the very first conversations through to implementation and then to learning together as a region. And it attempts to compile best practices and resources in one place. And these 9 steps themselves are familiar, but hopefully it's the integration and compiling of resources that's new. It dissects these steps into into 3 scales. So first, at the landscape scale planning, it includes convening authentic partnerships and developing plans to define goals and priorities. And those partnerships and the goals are carried through to site scale implementation, the second scale, which includes conceptualizing a project, then designing it and installing it in the ground, and those projects then getting continually maintained and monitored. And then kind of stepping back to the regional scale, the lessons learned from the landscape scale and the site scale fuel regional innovation. And that includes connecting and learning as a region and then translating those lessons learned to adapt projects. So together, these layers create a feedback loop for continuous improvement, connecting the phases of planning, implementation, and innovation. And in our regional framework report, each of the 9 steps include a summary of current common practices and recommendations on how to improve, partners that need to be involved in those steps at a broad scale, existing resources and tools to support decision-making at each of these steps, as well as gaps where more resources and guidance is needed, and then real-world examples of strategies applying the best practices. So for the sake of time, I'll just use the plan step as an example to walk through what the framework contains for each of the 9 steps. So first we introduce the step. What is it? Why is it important? And in the case of planning, the purpose is to articulate a shared vision and goals and link those goals to other policies and priorities within that geography, and then to outline actionable steps for prioritizing and implementing projects, including how to allocate resources efficiently to meet multiple objectives. And as for where there's room for improvement at this step, sometimes planning across a landscape is missed entirely. And when the planning is done, it's often conducted within a single agency. So when that landscape scale planning is led in isolation, there's a greater risk of focusing on narrow objectives. So collaboration across agencies with other organizations is key to planning urban greening projects that deliver multiple benefits. And plans can also do more to go beyond gathering input from communities. So the prior convene step prepares planning for collaboration and integrating diverse perspectives. And so enabling planning to build a foundation to partner with and co-own a project or a plan with community representatives. Partners to include at the plan step include co-developing the plan with community-based organizations and tribes, including staff from across agencies to integrate those multiple objectives and bridge the plan to implementation, and then to apply technical support and recommendations from scientists and researchers. And we compile resources, just to name a few: Green Planet, Urban Invest, data from the Urban Displacement Project, and more. And we also list some important resource gaps to fill, like a tracker of existing and planned urban greening projects in order to start thinking about the interconnectedness of projects across a landscape. So again, these steps are not groundbreaking. and the resources we compile aren't new. Many projects and collaborations are already doing cutting edge work across the Bay Area. Many of you all in this room are likely involved in those cutting edge projects. And so those projects are the testing grounds for how we confront the same complex challenges that we're seeing over and over again in the region. So this framework just seeks to compile those bright spots and resources in one place and offer a common language. So now I want to talk more about the path to collaboration and innovation. If there's one central thesis that's come out of developing this regional framework, it highlights the need to scale up our planning and collaboration and the sharing of resources and lessons learned. So each of the 9 steps is important for implementing projects that deliver multiple benefits, but not all steps are put into practice equally, and some even get missed entirely. So like I mentioned up top, at the site scale, conceptualize, design, and install are inherently essential to any on-the-ground urban greening project. And that's not to say that there isn't room to improve how we incorporate multiple benefits at these stages, but it's important that these steps already have a leg up in that there's more capacity, systems, resources, and funding mechanisms in place now to implement these steps, even if they need improvement. Then the further we get from those core 3 steps, the less commonly they're applied. So we heard a lot from practitioners that maintenance is commonly considered essential to project performance and longevity, and yet it's also sorely under-resourced and understaffed. And then government entities, particularly those with more resources, are developing more large-scale urban greening and green infrastructure plans. The steps that are receiving the least focus are those that are furthest from those core site scale steps. That's convene, monitor, connect and learn, and adapt. And these are also the steps that are essential to the deeper, more cross-cutting partnerships and the learning and adaptation. So that's what's needed to implement a next generation of urban greening. And so just to walk through what these steps can offer, Convene is about laying the foundation to build and also fund a truly collaborative landscape scale plan through authentic partnership. And convening diverse groups prepares the region or a geography to align around urban nature goals and strategies. And monitoring is what's needed to collect the information that we need to learn from our projects and adapt them. And then creating a regional community of practice to connect and learn is what would enable us to share lessons learned and share resources and also to collectively problem solve. And this connecting and learning enables practitioners across the region to access the best available information and then adapt their planning and implementation approaches. So just to drive home the point, we need to set a foundation for deeper collaboration and set up systems for collecting, distributing, and applying the best available information. And it comes down to having the time, the funding, and a central hub to fuel the regional innovation. So I'm going to now pass it to Karen to introduce SFEI's initiative to build a home for that collaborative work.
Thank you, Lauren. So yeah, we have developed this new initiative called the Urban Nature Collaborative, where we're trying to link science and policy and practice across the Bay Area. We're running a little behind, so I'm going to go through these slides pretty quickly. We do have breakouts after this, and I'd rather have more time for that, for conversation. So next slide. So this collaborative that we're envisioning is a collaborative network, as Lauren said, really to sort of help in that connecting and learning and adapting. and just making sure that we're all aligned regionally. And two of the main goals that the collaborative would achieve are setting regional goals for urban nature for the Bay Area. They don't currently exist. And also providing practical tools and information for folks that are working on urban nature projects. Next slide. So regional goals. Across the area, we have actually quite a few sets of regional goals. We have our upland areas, the Conservation Lands Network. We have shoreline goals for our tidal wetlands. We even have subtidal goals for oyster reefs and things like this, but we don't have urban nature goals for our developed areas. So that's a gap, and a gap we'd like to close. Next slide. And goals really do matter. So this is based on the Baylands Ecosystem Habitat Goals that set a target of 100,000 acres of tidal marsh in the late 90s. And then that really became an inflection point. And there's a noticeable uptick of restoration that happens after that point because people are working towards an established goal and everyone is kind of moving in the same direction. Next slide. So what we really would like to do is set a regional goal that is as multi-benefit as it can be in terms of what urban nature can accomplish in an urban setting. And so that's really looking at these three big categories, so biodiversity, water, and public health, and trying to find a target that is as central to all of those as possible. Obviously, not all locations will achieve this, but to big picture, try to come up with something that is in the center of this Venn diagram. Next slide. And so then this is the next main goal of the collaborative is the practical information piece. And as Lauren said, and the whole next-gen framework is built around landscape scale and site scale, and the same is true for the information that we're looking to provide. Next slide. So planning scale tools. This is for folks working at the watershed or city scale. And next slide. They need things at that scale. So goals and metrics, model ordinances, quantification of ecosystem services that are kind of regional in thinking. And then next slide. And then we have the site scale tools for folks that are working on, very particular project sites. This is my parcel within this much larger urban context, and they need different things. Next. They need more detailed plant palettes and street tree recommendations, design and maintenance guidelines, cost-benefit analyses that are at that scale. And it's really when you get both of these working together, the planning scale and the site scale, that you have the most impact. Next slide. So the other part of the collaborative is the collaboration. And that is to sort of have a tiered structure, not unsimilar to other work groups and other collaboratives. But there will be a core team, a steering committee, a technical advisory committee, and then work groups that are centered around different topics, all related to urban nature, that would be hundreds of people across the region coming together to think through these issues and problem solve together. Next slide. And the work groups so far, some anyway, that we've come up with, this is just a partial list. Stormwater GSI, based on what this presentation has been all about, but also heat island, urban forest, public health, bird safe design, streetscapes. There's many, many aspects of urban greening. And so we are hoping to rely on hundreds of experts regionally that would lend their expertise to these different topics. Next slide. And you can run through, I think this is a series of animation. Yeah. So, SFEI and you all working in your organizations, we are not alone in recognizing that climate change is real and that we need to think of some solutions to mitigate the effects. And so all of these different, both regional and state entities, are working on planning efforts, thinking about this. And so the collaborative really would, the vision is that we would be coordinating so that we're not siloed and not reinventing the wheel, but building on each other's work and really able to share that. Next slide. The idea also is that so Urban Nature Collaborative, kind of in that middle row on the left for the Bay Area, would also link up to a statewide alliance that was established last year. That's the three natural history museums and UC Berkeley, Chris Schell's lab, that could act as a statewide umbrella of not only our Urban Nature Collaborative here in the Bay Area, but what if there also was one in Los Angeles and San Diego, Sacramento, Fresno, etc. And we were all able to sort of stay connected and learn from one another, not just within each region, but across the state. No doubt LA is doing innovative things that we could learn from and vice versa. Next slide. This is our SFEI leadership team. Next slide. And then the rest of our urban nature team and the different areas of expertise that we bring. Next slide. The conversations that we've been having have gone quite well with the different partners here regionally. And these three so far, and hopefully there will be a few more, have agreed to sort of be advisors to us. We can pick up the phone, connect with them, and also stay aligned with them and their efforts as part of that collaboration. Next slide. And so really we see this as an emerging initiative for the Bay Area regionally. We see SFEI as being a convener and being able to facilitate this effort. And we would love either now if we have time or the breakout or just reach out afterwards. We'd love to hear your perspective on any thoughts that you have.
So just as a reminder, just as a really quick wrap up here for folks, this project is wrapping up on December 31st of this year. So we're going to be updating the project website with lots of stuff, including the GSI monitoring results reports, the manuscripts as they get published. We'll have implementation project details. We'll have the watershed plan, and the regional framework is up right now. So this is the QR code for the regional framework. If you want to take a look at that, please do send it to your friends. It's the holidays, gift it around. And then Lauren on the next page, we'll keep the QR code on the next page, don't worry. Just want to say a really big thank you. All of you here that have been attending these forums over the last 5 years have really contributed substantially to the framework and to the products that are coming out of this project. And we couldn't have done it without you. So thank you. And again, another special shout out to Will Logston and to Lauren Chavez from the city of San Francisco for all of the work that they've been doing and the matching funds that they provided so that we could actually do this project. And just, yeah, thank you also to the SFEI team for all of the work that you've done over the last 5 years and for pulling all of this together here and for this project. So thank you so much, everyone. Please feel free to reach out to any of us on the project team if you have questions, if you have thoughts about those questions that we asked in the breakout sessions. Please feel free to get in touch, and we look forward to working with you in the future, hopefully under the umbrella of the Urban Nature Collaborative. So thank you all very much. Have a good rest of your Monday.
Bye-bye. Thank you.
Bye.
Thanks so much.